Picture two identical wristwatches. Yesterday, they ticked side by side on a desk in London. Today, one of them has just returned from a round-trip flight across the Atlantic. You press their crowns together. They disagree by a few millionths of a second. No gears slipped. No battery faltered. Time itself, usually so loyal, has played favorites. Why? In everyday language, we treat time like pavement, flat, universal, the same beneath every shoe. Relativity paints a stranger street. Time dilation is the simple idea that clocks in motion, or parked deep in gravity, run at a rhythm slightly different from the one on your kitchen wall. It's not metaphors, not illusions. Literal seconds stretch or shrink depending on where you go and how fast you travel. Think of a checkout line at a bustling cafe. The barista serves the front customer right away, while those farther back inch forward. Everyone experiences the same cafe, yet their wait feels different. Swap customers for clocks, trade espresso steam for high speed or strong gravity, and you've met time dilation. Let's step onto a sleek, midnight blue train. Over each door hangs a light clock. A photon ricochets between two mirrors, tick-tock with every bounce. To a passenger sipping tea, the light simply bobs up and down. But viewed from a hill beside the track, the train rushes past, so the photon traces a longer diagonal path. Longer path, same speed of light. The hilltop observer must conclude each tick lasts a fraction longer. The faster the train, the greater the stretch. Numbers anchor the wonder. A commercial jet cruises around 900 kilometers an hour. Aboard that plane, time slows by roughly 20 nanoseconds. During an 8-hour flight, 2/100ths of a microsecond. Invisible to human senses, yet perfectly real. In 1971, physicists Haffel and Keating carried 4 suitcase-sized atomic clocks on east and westbound trips around the world, and the clocks were compared to twins left in a basement lab. Their readings parted ways by tens of nanoseconds, exactly the amount Einstein's mathematics predicted. Special relativity had climbed off the chalkboard and stamped today's date on an airline ticket. Speed isn't the only sculptor of seconds. Gravity, too, bends the rhythm. Imagine Earth wrapped in an elastic grid. Near our planet's surface, the grid is pulled tight. Higher up, it relaxes. A clock on the ground feels that tension and ticks a hair more slowly than one atop a mountain. Climb, and you literally outpace time below. The first laboratory proof came in 1960. Robert Pound and Glenn Rebka placed a gamma-ray source at the top of Harvard's Jefferson Tower and a detector at the bottom. Photons falling just 22 meters gained a whisper of energy. The tower's foot experienced time ever so slightly dilated compared with its crown. Today, your phone navigates rush hour traffic thanks to gravity's clockwork. GPS satellites orbit 20,000 kilometers up where Earth's grip is weaker, so their onboard clocks race ahead by 45 microseconds every day. Motion slows them by 7 microseconds. Gravity speeds them by 45, leaving a net 38 microseconds to correct. Engineers pre-offset the satellites. Without that tweak, your map dot would stray 10 kilometers each sunrise. Stronger gravities, stronger effects. Stand beside a neutron star, and an hour for you might equal 10 for a colleague orbiting 1,000 kilometers away. An extreme version of the mountaintop tower, written in starlight and tidal forces. Though jets and satellites dramatize the tale, time dilation already threads through civilian life. Next-generation 5G towers carry chip-scale atomic clocks, so their signals stay in precise phase. A necessity because nanosecond slips mean dropped data. At the Olympic 100 meters, photo finish cameras time stomp runners to millionths of a second. Judges adjust for Earth's rotation and gravitational potential to keep records impeccable. High-frequency traders synchronize servers between New York and Chicago to squeeze microseconds from transactions, enough to matter in finance. Even your digital photos owe a nod. CMO's image sensors rely on clocked charge transfers whose timing stability, set against tiny gravitational gradients inside spacecraft, shapes blur-free views of distant worlds. Project the idea outward, and the universe grows even stranger. Near the event horizon of a black hole, an astronaut could watch the Milky Way whirl by in time-lapse, days for her becoming millennia for distant observers. Future fusion-drive starships cruising at half the speed of light would grant their crews a biological discount, aging perhaps for years while Earth spins through 5. Pulsar timing arrays. Those galactic metronomes we use to hunt gravitational waves must fold in relativistic delays as neutron stars wind down. In cosmic bookkeeping, every clock is provincial. The only universal statement is that none of them agree. Will your smartwatch desynchronize if you jog around the block? Not remotely. The effect scales with v squared per c squared and with gravitational height differences. Walking speeds and household altitudes shave picoseconds, far below any consumer sensor. Time dilation matters when velocities graze orbital, or when altitudes scale mountains and satellites. Daily life remains safe from relativistic jet lag. So the next time you glance at a clock tower, remember, its hands march to a rhythm ever so different from the one in your pocket, and both diverge from the tick aboard the jet overhead. In our next crash course, we'll spiral into the wild spin of black holes and how rotation twists spacetime itself. Dive in. Your takeaway in one sentence? Motion and gravity stretch seconds, fly fast, climb high, or fall toward a neutron star, and you'll live a subtly different tomorrow.